All right, so we're going to go over this bat problem here. So at 6 p.m., there are 120 bats in the cave. So I already wrote that part down. Bats enter the cave, modeled at a rate by E of T. Okay, so we got that guy there. I got that one as Y1 in our calculators. So maybe you want to kind of mark that on your paper so you know which one's which as well. And leave the cave at a rate modeled by L of T. So I got that as Y of 2. Both of these, it doesn't really say it, but if bats are entering the cave, wouldn't that be bats per minute?
It does say it. Both
It
functions
does
are
it?
measured in bats per minute.
Oh, I just gotta keep reading, huh?
Yeah, just keep reading. And time t is measured in minutes after 6 p.m.
Which is a little bit different than our B problem that we just did, because I think that one we had time was in hours. Okay, so now we got time in minutes after 6 p.m. The models are valid for the time interval 0 to 15. All right, so it's going to be basically minutes after 6 p.m. So it's going to start at 6 p.m. and it's going to go to 6:15 p.m. All right, so number one, how many bats enter the cave between 6 p.m. and 6:10 p.m.? Okay, so if we want to know how many enter the cave, we want to use E of T. So we want to take the integral from 0 to 10, since we're going from 6 p.m. to 6:10 p.m. of E of T dt. Okay, in your calculator, you should just be using Y1. That's really all the work you really need to show for number one.
So there's our E of t rule in Y1. Make sure and get your decimals in there in the right spot. Make sure you're in radian mode. And then we can just go to a home screen, math 9, from 0 to 10, alpha trace Y1 with respect to x. And you should get 426.6 repeating. However, it did say in the problem, in parentheses, calculator active problem round to the nearest whole number if talking about the number of bats.
Oh, I missed that part. Okay, so this is what it's going to give you if we need to round to the nearest whole bat. This is going to be 427. So 427 bats. Enter cave. From 6 p.m. to 6:10 p.m.
So on the B problem, it didn't say anything about rounding, so we kept everything to 3 digits the whole time, even if we were talking about the number of bees. But typically, if you're talking about people or animals or things, cars, they will say round to the nearest whole number. So this one's kind of practicing that. So we've kind of given you some of both with these big problems.
But definitely only round to the nearest one if they ask.
Yes.
Okay? Don't just automatically assume you're supposed to round, because I know grading a couple of your guys' problems, you were rounding when you weren't supposed to be rounding. So that's just something to keep in mind here. Number two, how many bats leave the cave from 6 p.m. to 6:10 p.m.? Well, it's going to be pretty much the same thing, but we want to use our equation L of t now, which should be y2. We're going to integrate once again from 0 to 10. And that's really all the work you need to show.
Remember, when we're just talking about the number of bats entering or leaving, and we have the rates of change for bats per minute entering and bats per minute leaving, you have nothing to do with the initial condition here. So when we math 9 this guy, we end up getting 227.774, but that would round to
So about
228 bats.
228 bats leave cave from 6 p.m. to 6:10 p.m. All right, awesome. Let's move on to number three. How many bats are in the cave at 6:10 p.m.? Yeah, so normally we use like A of t to kind of calculate this, but I already know in their next question they're going to have us write an expression B of t, so I'm just going to use B of t now. So B of t is really going to equal the initial number of bats, which was 120, plus the integral. So here we're going to have the integral of our bats entering minus our bats leaving, L of x.
Remember,
dx.
you can do y1 minus y2 and store that in y3.
Okay, so we want to know at 10 minutes, so I'm going to have B of 10 here technically. And I'm going to go from 0 to 10. Okay, so we really already found E of t, the integral from 0 to 10, and we had already found the integral of L of t from 0 to 10. So you could do 426.667 minus 227.774 and just add 120 to that.
Or you could type it back in, and I got 318.893. But we're talking about number of bats, and here we're talking about a specific time, so the initial condition did matter. So we got to round to the nearest bat.
There will be about... Okay, so that's going to round up to 319 here. So this is going to be about 319 bats in cave. Okay, not all the time, but at 6:10 p.m.
Definitely restate your time.
Mm-hmm. Sweet, that was number 3. All right. Number 4, write an expression for B of t that would represent the number of bats in the cave at time t. So we really pretty much already did that. I just need to replace my 10s with a t. Now it's going to work for basically all times. So that's all we need to do for 4 is say B of t is going to equal 120 plus our integral. Okay, so from 0 to t here, so these cannot be t's, which is why I already had e of x minus L of x dx. Okay, that's all it's really asking you to do on number 4. Let me erase here, make some more room.
Sometimes I will show this as B of 0 for the bats at the time of 0. If you like that twist like I think about, because then you know this time has to match this lower boundary time. And this time, which is a variable because I want the bats at any time, has to match the upper boundary time. And then on the next step, replace B of 0 with the 120. Either way. Cool, number 5?
Yeah, number 5. We got to figure out what B of 10 minus B of 5 is. Okay, so we already had our equation over there for B of t, which I erased for some silly reason. I'm just going to rewrite that. B of t really equals 120 plus the integral 0 to t. E of x minus L of x dx. Okay, we're going to use that for pretty much every problem here on out. So if I want to figure out B of 10, I just plug 10 into all of this. So this is going to be 120 plus the integral from 0 to 10 of e of x minus L of x dx. Okay, so that's really B of 10 here, and I want to subtract all of B of 5, where I'm just going to plug 5 into my equation. So it's going to be 120 plus the integral from 0 to 5 e of x minus L of x dx.
And remember, you guys, that we had just done B of 10. So I did a similar thing that Hernie did, but since I just had my answer for B of 10, the 318, without even rounding error, I just said minus, so it would take that previous answer and subtract. I did parentheses, like Hernie's big brackets, right? And then did, okay, I have to find the B of 5 answer. So I did the 120 for the initial, plus what I accumulate from 0 to 5 of the rule that's in Y3, because the rule in Y3 is where we're thinking that rate in minus that rate out. And you should get 28.017, or...
Okay, so we got to think about what this is actually representing. So remember, B of 10 is really the number of bats in the cave at 6:10 p.m. And B of 5 is really the number of bats in the cave at 6:05 p.m. So if we take the number of bats at 6:10 and subtract the number of bats at 6:05, that really means there were about 28 more bats in the cave at 6:10 versus 6:05. I believe it's asking you to talk about what that is.
Yep, in context of the problem.
Yeah, so I would say there are about 28 more bats. Since this is positive, if it ended up being negative, then there'd be about 28 less bats in the cave. But here it was positive, so there are more bats in cave at 6:10 p.m. than at 6:05 p.m. All right.
And another thought is, I think we talked about this a little bit on the B problem. Sometimes maybe you wouldn't actually be able to find the answer, let's say, but they would say maybe on something that you couldn't calculate for whatever reason. What would this mean in context to this bat problem? So another way to think about it is, well, I don't know whether or not when I subtract I get a positive or a negative to know whether the bats are bigger or smaller at whatever moment between the two time frames, but you could say it represents the difference of the number of bats between times 6:10 and 6:05 p.m. So it's that difference between the two.
Yeah, like net change.
Yeah, the net change.
All right, number 6.
We're rocking this problem, Hernie.
Heck
Boom.
yeah. Number 6, we got to calculate b prime of 10. Okay, so before I find b prime of 10, I'm just going to find b prime. So understand b prime, this is my equation for b of t. I just want to take the derivative with respect to time. So b prime of t, so the derivative of 120 goes away. The derivative of an integral basically just cancels, and we're going to be left with e of t minus L of t. Okay, so understand that was really just y1 minus y2. So maybe in your calculator you want to say y3 equals e of t minus L of t. Just something to keep in mind there, which is y1 minus y2. Okay, so if we want to find b prime of 10, what we're really going to do is, if this is in our y3, we can just say y3 of 10.
Or if you went ahead and put in y1 of 10 minus y2 of 10, it's going to give you the same answer. 5.526.
Okay, so remember our units. B was representing the number of bats in the cave. Okay, the derivative is going to be bats
Per
minute.
minute.
Right?
That's per
Yeah.
minute.
Bats per minute.
And since this answer's not about the number of bats, it's about what's happening when you subtract the rate in minus the rate out at time 10, and this is a rate, they probably won't have you round. It only said to round when you're talking about the number of bats. This is not bats, it's bats per minute. So we're going to leave it like that, but we have to interpret it in context.
So number of bats in cave is increasing at a rate of about 5.526 bats per minute at 6:10 p.m. Okay, make sure you restate the time because it's not always going to be increasing at that rate. It's only increasing at that rate at 6:10 p.m. specifically. All right. Number 7. Is the number of bats in the cave increasing or decreasing at 6:10 p.m.? Justify your answer. So basically it's asking the same thing as number 6 was. Okay, just kind of getting you to understand there's 2 different ways they might ask this question to you, but it's the same exact thing. Okay, if we want to know if the number of bats in the cave are increasing or decreasing, we would want to find b prime of 10. We would find it's positive. Okay, so maybe here we would say the number of bats in cave is increasing at 6:10 p.m. because, and then you could say b prime of t, or I'm sorry, b prime of 10 is greater than 0. Or you could say that it's positive. Okay, but it's really asking the same, pretty much the same exact question, but here your justification is just going to be slightly different. All right, number 8, I believe, is going to be some EVT.
Yeah, we love EVT.
EVT! Some of you are still copying from the website on EVT. But 8, well, what time for t between 0 and 15? So we are using that entire kind of duration of this problem. will the population of bats in the cave be at a maximum? Okay, and we want to know how many bats are in the cave at this time. Justify. So we want to know the maximum number of bats in the cave. Understand B of t represents the number of bats in the cave, so we're going to have to first do our endpoints. Okay, so we're going to have to find B of 0, and we're going to find B of 15. We also are going to need to figure out when B prime equals 0, or since it's specifically asking for a maximum, you could exclude possibly some of these and just figure out when B prime changes from positive to negative.
Okay.
All right, so remember B prime is just going to be E of t minus L of t, which we have stored as Y3.
So we've done this a few times, and hopefully you're starting to get the hang of the calculator work on this stuff. So if you just deselect your equal signs on Y1 and Y2, so you're not talking individually about graphing just the rate of bats per minute entering and the bats per minute leaving, but you are graphing that part where it's rate in and rate out. So you're only going to graph Y3. I just set my window from 0 to 15, because that's the time from 6 to 6:15, going by ones. And because we're really looking for where we equal 0 on our derivative and, in particular, change from positive to negative, I just did negative 10 to 10 going by ones. And the graph looks like this. And if you turn the other two off, then you can focus on just this graph. So it looks like we have a time where we are switching from positive to negative. And if we do second calc and find that 0, to the left bound would be above there, to the right bound would be below. We hit guess, and I got a time of 7.1811821. Remember, we don't want intermediate rounding, so don't round right now. The next spot, you guys, is the wrong change of sign. You're switching on your derivative graph from a negative to a positive. So that would be a local min, and maybe it's the absolute min, but if we're talking about the maximum number of bats, we don't care about that one. So we better start over, second trace option 2 to calculate the 0, but go over to that last one. And to be the left bound again, is going to be above there. To be the right bound, it's going to be below. And you should get this time a time of 11.587411. Hernie, did you get that as well? Yeah.
Yep.
Awesome. I had already ran on the home screen because we knew the endpoint of 0 was going to give us 120. That was the initial number of bats. I got 173.333 for the bats at the other endpoint at 6:15 or at time 15. And now you can get lazy, you guys. If you forgot about like going up and dragging these down, you could drag them down. You got the initial condition considered. You have the integral from 0 to start at 6 to wherever you want to go. We're just going to switch that time on the upper boundary every time of Y3, right? Do it that way so you don't mess up with your subtraction or anything. And now we just want to put in those unrounded times to see which one produces the maximum. So all I did was type over my 15 to type in the 7.1811821. So this time I got, for that first spot where B prime switched from positive to negative, 333.933. And then the last one with the time of 11 point something, 587411. We get to 3 places, dun, 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 327.786. Look at that.
Make sure you guys do say something about B prime changes from positive to negative, which is going to be the reason why you rule out that other option. Because I do know on that one trig problem with EVT, you got a point for considering both the minimum and maximum value, where B prime would have equaled 0. So at least just try to mention that if you can. So this question is actually asking for both when and how many. Okay, so we would say the maximum number of bats in the cave is about, so remember here we're once again talking about the number of bats, so we want to round that answer, is about So this was our maximum here, 333.933. So we're gonna have to round that guy up. So it's gonna be 334 bats at time, and just use that t value. Okay, don't try to say 6:07.181 p.m. Okay, so just say at time t equals approximately 7.181.
Yep.
All right, that was fun. And then you said you want to take number 9?
Herney's setting me up and making me take number 9. Okay, so there was a problem like this, you guys, on the B problem as well, where it's asking when, so we're going to solve for time. When are the bats leaving the cave the fastest? So we're not considering both the rate in and rate out. We just want to talk about, okay, we got to think about this. We have this rule that we stored in Y2 of L of T, and that's about the bats per minute leaving. And we want to know when they're leaving the fastest. So there's kind of a pre-calc way to do this problem and a calculus way to do the problem. I mean, you're supposed to do it the calculus way. I think some of you might luck into doing it the pre-calc way. But if I want to know when the bats are leaving at the fastest rate, don't I really want the maximum of this rate of change? So if we just think, okay, how do we find maximums in calculus? Oh, we hope that we can do EVT because that's a little bit more straightforward than a whole sign analysis, right? We test the endpoints and we test where the derivative equals 0 and changes the correct way. For a maximum, we would want, just like we did on this last problem with the maximum number of bats, the derivative changed to positive and negative. But we're talking about the derivative of this derivative. So it's we would want to find the derivative of L of T and find where it equals 0 and changes from positive to negative. So this is the more calculus way to do it. I know that this is a good marker, so I'm still in this one. Okay? So I'm just going to write down, we want to find where L prime of T equals 0. I'm not really going to find this by hand, you guys. This would be gross. It would be product rule with chain rule and ugh. We're not going to do it by hand. I'm going to teach you something that we haven't really taught you maybe necessarily as formally. We usually teach it in the review time of year. You guys have just kind of had to learn that a lot on videos. And not only do we want that, but also where L prime of T changes or switches from positive to negative. And since we still know we're talking about just this time from 0 to 15, if we're still thinking about the candidates, once I find this set, right, then I still want to test the 0 and the 15 into that too. And doing the candidates test is how you justify with EVT. You have to give them a conclusion because they're not going to just assume you know what's biggest and smallest. So this is going to be crazy calculator work. So we already have Y1 turned off. We're going to leave Y1 off. But I'm going to go back and turn Y2 on. No, actually, I'm going to leave Y2 off. I lied. I'm going to turn Y3 off because I don't want Y1 minus Y2. And I'm going to go into Y4. You ready for this? You ready for this, Mr. Herney?
Yep.
Have we ever shown them this before?
I haven't, so I know
Okay,
that.
if you want to graph a function's derivative, you can actually graph it, which is pretty crazy, in general. So even though it's not a specific time, you can graph it in general. So you're going to hit Math 8. This only works in a graphical way. And you're going to go, I'm going to graph the derivative with respect to x, so I filled in my x, of the leaving rate of change in bats per minute. Oh, that was stored in Y2, so alpha trace Y2. And I'm going to do that evaluated with respect to x. It's evaluate x equals x, and then it does it in general. Now, this is going to take the calculator some time to think, so you have to realize if you don't turn the rest of the junk off, you're going to get nowhere because it's going to have to think pretty hard to do this anyway. What it's really doing is calculating each point's rate of change, each point's slope. So it's graphing the little slopes of the tangent line and then connecting them all. Oh, look at that, Mr. Herney. Now you come run the calculator stuff because there's actually, I think, quite a few times where it changes. Yeah. So we're looking for where that derivative, L prime of T, it's the rate of the rate, equals 0 and changes from positive to negative because we want to know where the bats are leaving the fastest. That's the absolute maximum of this rate of change, where they leave the fastest. And Mr. Herney will kind of show some of that, calculating, finding the 0 thing. I don't know if there's some spots where it changes the opposite way, but I got quite a few spots where it changed from positive to negative.
So now where it changed from positive to negative, we're looking for the zeros. Okay, so here I'm on my left bound. Hit enter. Oops. Okay, and we want right bound. There I'm right of there. Hit enter. Guess. Just enter since I only have 1 0 in there. So that's going to be my first one. 2.499. Sweet. Okay, so we get to do this several times. Okay, so once again, it's asking for left bound. We don't care about where it's changing from negative to positive. Okay, so I can keep going over to the right there. Oh, too far. Okay, so there I'm definitely left bound. Hit enter, right bound, go to the right a couple clicks. And there's our next one.
8.1033 blah blah blah.
Yep.
Sweet.
So we get to do this again, find another 0. Left bound, so we don't care about our next one because that one's changing from negative to positive. Okay, so I'm just going to scroll to the right some here.
And I think the last one you should get 14.278
That is correct.
once we get there. Bless you.
Got the Rona.
No Rona. Okay, cool. So now, just like we do, if we were doing a regular EVT problem, it's not really any different. It's just like we're running EVT on the rate of change. We're going to plug all of those into the original rule L of t. So if I plugged in 0, one of my endpoints, into L of t, you guys, that would be 4 times 0 times e raised to the blah, blah, blah times 0. But it's a product, so it's going to be 0. So this would be 0 bats per minute leaving at time 0, at time 6, when we started all this information. So that's probably not going to be my maximum, right? So now I'm going to plug in 15. Remember, we stored L of t and y2.
So Y2 of 15 is going to be 83.054.
So 83.054 bats per minute are leaving at time 15. That's our other endpoint. We're looking for the maximum. So now we're going to try these spots that were the critical points, right? The critical points where our derivative L prime of t was equal to 0 and change the correct way for maximum.
Okay, so Y2 of 2.4 whatever is going to give us 13.488.
Okay, well that's smaller than the endpoint of 15, so we're like, that time's out. That was only a couple minutes after 6 o'clock anyway. So now we're trying this one 8-ish minutes later.
So Y2 of 8.1033 is going to give us 0.621.
Okay, and then the very last one at 14 minutes, almost to our other endpoint of 6:15 p.m.
Give us 93.697.
Okay, so we just got to kind of wrap it up like we typically do with EBT, right? So with EBT, we have to kind of answer the question. It only asks us when, so we only had to find the time. So therefore, the bats are leaving the cave the fastest at t is approximately, well, this time gave us the bigger number of bats per minute leaving. So 14.278 minutes after 6 o'clock p.m. Because that's not what's happening at all the times. That's just what's happening at that moment, and that's when the bats are leaving the fastest. Remember, these all represent bats per minute because they're in a rate of change rule. They're in the L of t bats per minute rule. So that's the very calculus way to do the problem. I did say that there was kind of another way to do the problem. So if you can kind of reason your way through that it's the maximum of L of t, and you didn't know, because we really haven't talked about how to graph the derivative, and you didn't know how to do that like math 8 in y4 thing. So I'm going to go back and turn that off. And I'm just going to turn on my L of t rule, which is the rule that's in y2, right? And I still want my window probably from the 0 to 15 going by ones, but now I'm like actually going to graph this rate of change. So, I mean, I'm kind of cheating because I already know like what the biggest numbers are, but even if you didn't know and you thought, well, I don't know, maybe the bats per minute could eventually be up to like 100-ish. Or start with something, you can always adjust it if you can't see. We're actually going to like look for the maximum on the graph, like the pre-calc idea.
Zoom fit.
Or you can zoom fit, okay? I did -10 to 100 going by tens because I'm not a whanny and can try and think my way through it. Okay, so I'm actually graphing the L of t graph, only the one that's in Y2. And do you see that like the tippy top point, that's the absolute maximum on that graph? So then you could do, which they don't really test on the AP exam, but this is kind of a cheat way to do it. Do second trace and go into calculate, but run option 4. So I know you guys are really used to using option 2. Sometimes we find where two graphs intersect, and that's option 5. And those are the two that are tested on the AP exam. But we're going to choose option 4. And then I'm just going to scroll over to the very edge on that right edge. I can tell it's that same time, right? 14 point something-ish. And then to be to the left would just be a little bit on the side of that maximum. Go a little bit to the right for the right bound. And yes, Mr. Calculator, guess. And we get the same value. So that's kind of the pre-calc cheat way to do it. The idea is you can still run EVT to find a maximum of a rate. You just have to like take the derivative of that rate and find where that equals 0. And then whichever one you're looking for, find the appropriate sign switchage. How do you like that? Sign switchage. Okay, so that's probably the hardest part of the bat problem. Number 10.
Number 10. So I know from grading your guys' homework, you guys have been kind of confusing number 10 with number 11. So pay attention to the wording on this. Find the average value of L of t on the interval 0 to 10. Well, that's just going to be fave of L of t. So for fave, what we want to do is just 1 over 10 minus 0, or just 1 over 10. And then we're going to integrate L of t dt from 0 to 10. Okay, that's all the work you need to show on that. And you just type it into your calculator.
Remember L of t was in Y2? Or if you want to type 1/10. And you should get approximately 22.777.
Okay, so let's think about our units here. Are we going to have to round to the nearest whole bat, or what are we doing here? So remember, L of t is really bats per minute. And we're going to integrate bats per minute with respect to time. And when we do that, we're going to be left with just bats. However, we have 1 over time out front, so 1 over minutes. When we end up multiplying that back in, we end up with units of bats per minute. Okay, let's go back to the question. It was asking us, find the average value of L of t. So the average value of L of t, well, L of t were in bats per minute. Our answer better be in bats per minute if it's the average value of L of t. And that's all you got to do. So we're not going to round this. It's going to stay 22.777 bats per minute. So what that's really saying is there's about 22.777 bats per minute leaving the cave from 0 to 10 minutes.
Or from 6 to 6:10 p.m. Which is different than what 11 is asking.
Yes. Okay, the word, it's only like 1 or 2 different words. Okay, but it means something entirely different. Find the average rate of change. Average rate of change. Average rate of change of L of t on the interval 0 to 10. That's when we want to do L of 10 minus L of 0 divided by 10 minus 0.
And you guys remember on AROC, you have to show and demonstrate a difference quotient. So if you're running AROC on L of t, but L of t is bats per minute, but you're dividing by minutes. Oh.
Okay. Also, guys, we know that 10 minus 0 is 10. Okay, but show the difference quotient on AROC every single time. Okay, so show that 10 minus 0.
So I type that in. Remember, L of t is in y2. So y2 of 10 minus y2 of 0 over 10 minus 0. And you should get 3.047 approximately.
Okay, now let's talk about our units again. L of t is measured in bats per minute. And we're dividing by really what was minutes. So this is bats per minute or bats per minute squared. All right. I think that's all we need to do.
Yep.
Want to add anything?
No, it's good.
Sweet.